So, now we will enter the 6th week of this course, and in this week we will be talking about second order ordinary differential equations. Okay. And actually the 6th, 7th and 8th weeks all will be talking about second order differential equations. Okay. So, today I will just get started with second order differential equations, and during this week we will be talking about homogeneous and non-homogeneous equations. So, in the first lecture we will talk about the types of second order differential equation and what the solutions look like. Then in the next lecture we will talk about homogeneous second order differential equations and what are the properties of their solution, what are the properties of the solutions of homogeneous second order differential equation. Then in the third lecture we will talk about homogeneous and non-homogeneous equations, and how we can what are the tricks you can get you can use to solve homogeneous equations, and then we will talk about a method of solving non-homogeneous equations called variation of parameters, and then finally we will have some practice problems. Okay. So, let us start the lecture. Let us start talking about second order ODEs. So, a second order differential equation, okay, it is characterized by a second derivative. If you have y as a function of x, then second order differential equation has d square y by dx square. Okay. So, then it has a second derivative. Second derivative is the highest derivative that appears. And second order differential equations are very common in all branches of science and engineering. You have the spring equation, okay, so that is a second order differential equation. You can have the quantum mechanics, the Schrodinger equation is a second order differential equation, and so on. So, just for example, if you take one particle moving in 1D, okay, then the quantum mechanical equation, the Schrodinger equation for this particle has a form minus h bar square by 2 m d square by dx square of psi of x plus v of x psi of x is equal to some constant E times psi of x. So, this is the time independent Schrodinger equation, okay, or this gives you the stationary states where energy is fixed. So, E is constant. If you look, this is a second order differential equation in the variable for the quantity psi. So, psi is your dependent variable and x is the independent variable, and V of x is some function of x which is known as the potential energy function. Okay. So, this is a second order differential equation because the highest derivative of psi that appears is second derivative. So, in the other terms you do not have any derivatives of psi and you just have psi to a constant. Another example is what is called the diffusion equation. Okay. So, here you have a constant, you have a concentration which depends on x and time, okay, and what you write is that you write the partial derivative with respect to time, this is equal to d times, now x is just, let us say I am taking the 1D diffusion equation, one dimensional diffusion equation, then this is just d square c by or dou square c by dou x square, and again c is a function of x and t. So, the highest derivative of c that appears is a second order differential equation. This is actually a second order partial differential equation, okay, and the highest partial derivative with respect to t that appears is first order. Okay. So, this is one example. The wave equation will have a d square by dt square with a very similar looking right hand side. So, essentially these sort of equations are something that you see all the time. I'll just add one more equation. So, the simple harmonic oscillator if you have let us say one dimensional again. So, then you have d square x by dt square. So, times the mass. Okay. So, this is the force on the particle attached to the spring, and this is equal to minus k times x. Okay. So, where k is the spring constant. Okay. So, now this is a second derivative of x. Okay. So, this is also a second order differential equation. Okay. Now there are various types of second order differential equations. Okay. I will just mention a few types of second order differential equations. Okay. So, you can have second order differential equations that are let us say homogeneous, or inhomogeneous or non-homogeneous. Okay. So, what does a homogeneous second order differential equation look like? Okay. So, I will just write one form. So, suppose I write my second order differential equation as y double prime plus a of x y prime plus b of x y equal to 0, and similarly a non-homogeneous equation will look like y double prime plus a of x y prime plus b of x y equal to c of x. So, now here I have used y prime as a notation for dy by dx and y double prime as a notation for d square y by dx square. A of x, b of x and c of x are some functions of x. So, any differential equation that has this form, where you can write y double prime plus some function of x times y prime plus some function of x times y equal to 0. This is called a homogeneous equation. The reason it is called homogeneous is because each term has y up to power 1, y or any of its derivative up to power 1. So, this has the second derivative up to power 1, this has the first derivative up to power 1, this has the 0th derivative or y up to power 1. So, the power of y or any of its derivative is the same for each of the terms. Okay. So, therefore, it is called a homogeneous equation, and in particular this is called this type of equation is called a linear homogeneous second order differential equation. Okay. So, I will just mark. So, this is an example of a linear homogeneous second order differential equation. The reason we said it is linear is because the power of y or any of its derivative in each term is 1. Now, the only difference between a homogeneous and a non-homogeneous differential equation is that you have this extra term c of x, which I have written as c of x. Okay. Now here again this is also linear. Okay, because the power of y in each term is 1 or 0. Okay, the maximum power of y is 1. So, this is also linear, but this is non-homogeneous. Okay, it is non-homogeneous because the right hand side contains it is not equal to 0. Okay, and it does not contain y to power 1. So, the right hand side does not contain y to power 1. So, there is a term that does not contain y or any of its derivatives to power 1. So, this is an example of a non-homogeneous equation. It is still linear because each term has y up to a maximum of power 1. Okay. So, we can think of second order differential equations, we can check whether they are linear or they are non-linear, and then you can check whether they are homogeneous or non-homogeneous. Okay. And there are some very nice properties of solutions of some of these equations that we will look at as we go along. Let us once again mention that we have linear versus non-linear Okay. So in a linear equation will look like y double prime plus something times y prime plus a of x times y prime plus b of x times y, this is equal to c of x. This is a general linear second order differential equation. It's homogeneous if c of x is 0. A nonlinear equation will have there could be many ways an equation could be nonlinear, but the simplest way I would say is if you have a of x y prime plus let us say b of x y square, okay, this is 0. Okay. Now, clearly this is a non-homogeneous equation because you have y square. Okay. So, the y square term is it is a non-linear term. Okay. Then you could have homogeneous and non-homogeneous. Okay. The homogeneous one is given by y double prime plus a of x y prime plus b of x y equal to 0 or c equal to 0, and in this case you have y double prime plus a of x y prime plus b of x y equal to c of x not equal to 0. Okay. So these are the typical types of second order differential equations that we will encounter. Further we might encounter some second order differential equations where the coefficients, where these functions a of x and b of x might have a specific form. Okay. So suppose a of x, b of x may be a constant. So we could have a second order homogeneous linear equation with constant coefficients. So this would be, so this would look like y double prime plus some constant, I will just write it a times y prime plus b times y equal to 0. So this is a second order homogeneous linear equation with constant coefficients. So it always helps to identify what type of differential equation you are dealing with, because for each type of differential equation there are very efficient ways to solve them. Okay. Now, what about the solution? So suppose you solve a second order differential equation, okay, then in general solution, so there could be a general solution. General solution will have two arbitrary parameters. Okay. And of course, you could have a particular solution. This will have no arbitrary parameters, arbitrary constants, you can just say constants, parameters or constants. Okay. So what the message is that if you want to get a particular solution, you need two boundary conditions. Okay. So you need not just one boundary condition, but you need two boundary conditions in order to get the particular solution. Okay. So let us just take one example just to illustrate this point. So if I take y double prime plus 4y equal to 0, okay, this is actually a simple harmonic oscillator. Okay, only thing, instead of d by dt I have d by dx. Okay, then I can immediately see that just by inspection y equal to sine 2x or y equal to cosine 2x or y equal to e raised to 2 I x or y equal to e raised to minus 2 I x are all solutions of this equation. Okay. So, each of these is a valid solution. You can verify. Suppose I take the first derivative of this, I will get 2 cosine 2x. If I take a second derivative, then I will get 2 into minus 2. So, that is minus 4 sine 2x. Okay. So, then you have minus 4 sine 2x and then you have plus 4 sine 2x. So, it is 0. Okay. So, similarly you can verify that the cosine and the e to the 2ix and e to the minus 2ix also satisfy. Okay. So, how do you write the general solution? Okay. So, in order to write the general solution, what you write is y is equal to, I will write it as C1 y1 plus C2 y2. In this particular case, okay, if sine 2x is a solution, even some constant multiplied by sine 2x is also a solution for this differential equation. Okay. And we will see in the next class that there is a certain property of this differential equation that allows you to write the solution this way. Okay. How do you choose y1 and y2? We have many choices for y1 and y2. So, the idea is that you can choose any two y1 and y2 that are linearly independent. Okay. So, you can take any two functions that are linearly independent. Okay. So, it should not be, one should not be a constant times the other, that is the only restriction. You can write the solution. Okay. So, one way to write the solution would be to take let us say you can take y equal to a sine 2x plus b cosine 2x. Okay. So, this might be one way, okay, where a and b are constants which are determined by the boundary conditions, okay, or y is equal to a e raised to 2 I x plus b e raised to minus 2 I x. Okay. So, you could also write it in this way, and in fact there are also other ways to write the solutions. Okay. So, now what we mentioned is that these two solutions sin 2x and cosine 2x have to be linearly independent. So, similarly e raised to 2 ix and e raised to 2 minus 2 ix are also linearly independent. Okay. So, there is a connection between differential equation and matrix. Okay. And we actually saw that in the classes during last week, where we actually used matrix methods to find out solutions of differential equation, and if you remember, we used it for a system of differential equations with constant coefficients, and notice that this is a second order differential equation with a constant coefficient. Okay. So, I can actually write this in a slightly different way. So, I can write this as, so we can rewrite y double prime plus 4y equal to 0. Okay. So, you define y prime equal to y1, okay, and or actually let me do it this way. So, slightly differently, I will write y1 equal to y and y2 equal to y prime. Okay. And you recall from last week that we said that this second order differential equation can be written as a set of first order differential equation with constant coefficients. So, if I take this equation, then I can write this as so y double prime is nothing but y2 prime. So, I can write this as y2 prime plus 4 y1 equal to 0, and the first and the other equation I can write this as y1 prime. So, this y2 equal to y prime, okay, y is same as y1. So, I can write y1 prime equal to y2. So, minus y2 equal to 0. So, in other words, I can write this equation in the following form. So, y1 prime y2 prime, Okay. So if I take these to the right, I can write this in matrix form. Okay. So y1 prime does not have any term that depends on y1, but it has a plus 1 that depends on y2. y2 prime has a plus 4 or it will have a minus 4 on y1, and it does not have any term that depends on y2. Okay. So this is my, and you have y1, y2. What we showed is that you can take the second order differential equation, write it as a pair of coupled equations, and you can immediately see that since this is just by matrix methods, you know that the solution looks like e to the lambda x, okay, where lambda, if lambda from this equation, so you will get lambda square plus 4 equal to 0, or you will get lambda is equal to plus minus 2i. So, the linearly independent solutions will look like e to the 2ix and e to the minus 2ix. You will have e to the lambda x, so it will be e to the 2ix and e to the minus 2ix, and you can find the corresponding eigenvectors and you can solve this equation. Okay. So this, I just wanted to illustrate this point that because this was a linear homogeneous second order differential equation with constant coefficients, okay, you could actually have just used matrix methods that you learned from first order differential equations and solve this system of equation. And notice that this solution is the same as what we had here, a e to the 2ix and b e to the minus 2ix. Okay. So I will stop here for today. Okay. So in the next class we will talk more about homogeneous second order differential equations.